problem you guys are going to see tonight. We're going to look at 5.1 stuff still. The first piece of it is just evaluating the function. And then every once in a while, it's like if, in this particular example, we're going to be talking about speeding and fines for speeding. And in this case, the equation is set up such that f of x represents the fine given with x miles per hour. So we're speeding, right? Every once in a while, maybe I know what the fine is, and I want to know how fast people were going. So we're going to talk about finding the inverse and how that'll help us. So hopefully we've done this since like Algebra 1 type stuff. And we'll just look at flip-flopping our variables, basically. Okay? So in this particular case, I want to know what is my fine if I was going 65 miles per hour. So we're going to plug in 65 for x, since x represents our miles per hour, minus the 560. Okay, 12 times 65 is 650 plus 130, so 780, maybe? So with the calculator, want to check me along the way? Cool, minus our 560 means our fine is $220. Awesome. Okay, so I know that if I was going 65 miles per hour in a 50, in the speed zone of 50, I would expect to be charged a $220 fine for speeding. Okay? Now, it asks us to find the inverse, and the inverse will help us because I want to know, well, if I'm, given a certain fine, how fast was I going? So if we find the inverse, we flip-flop our x and our y's from the original equation. To solve for our y again, we would end up adding the 560 and then trying to divide everything by 12. So we would see that our inverse function is this x plus 560 divided by 12. Okay, now in this case, f of x represents what our total fine, or what our miles per hour is, given a certain fine. And so we can plug in, if I know my fine is 172, how fast was I going? Okay, so 172 plus our 560, then divided by 12, tells us that we were going 61 miles per hour. Okay. So being able to find the inverse can be nice because now, instead of having to work through all those steps of adding and subtracting every single time, we can just have this equation set up where the speed equals something in relationship to the fine. Okay, so finding the inverse and manipulating these formulas is sometimes nice that way. So the first two you're going to have very similar to that, just setting up equations using the inverse because now we want to find the information the other direction. We'll go from there. So that's stuff that we've seen the last few days. Okay. So next thing we're going to take a look at is 5.2. Okay, 5.2 actually starts getting us into some of these exponential properties. How many of us have messed around with exponentials, adding, multiplying, all the exponents, those kinds of things? Okay, so hopefully this will be kind of review. If you're multiplying things that have the same base, okay, you can add their exponents. So let's see how that actually would work. So let's say I had something like b to the third times b squared. Squared. What does this actually look like? Well, b cubed is b times b times b. B squared is b times b. And so multiply together, how many total b's do we have now? We have 5 of them, which is where this comes into play. 3 plus 2. So this is our b to the 5th. Okay? So we have this total exponent. Now let's say we had division. Okay, very similar But with division now, let's say we had b cubed over b squared. I have 3b's on top, 2b's on bottom. We need to split apart. Okay. We're not taking notes. We're not focused at all right now. And we're distracting everybody else. Okay. All right, so I can cancel 2b's on top and bottom. So how many b's do we have left? Just 1. Okay, so this follows that same logic. We're going to take b to the m over b to the n. And so this would be b to the third minus 2 gives us just that single b. Okay? So if you can't memorize all these, which I hate memorizing a whole bunch of stuff, just understand what's actually going on and kind of, oh yeah, that's right. I've got b's on top and bottom. They can cancel because they're the same base. Okay? Powers to powers. So in this particular case, if this was our b cubed squared, basically I have 2 groups of b cubed. So this is like I have b times b times b times a b times b times b. Okay, so there's 2 groups of them now. So now when I look at it, there's a total of 6 of them. And so we have b to the 6th, which is exactly what we're talking about. This is that b to the 3 times 2. And so it's that multiplication step. Okay, so that's where that shortcut comes from. Now, if you have multiplication instead of a group, no addition, no subtraction. It's got to be all multiplication. You can apply this exponent to all the parts. Okay? So in this case, you can split that apart as a to the n times b to the n. Okay? But that's different than like when we're dealing with quadratics where you had like a plus b, the quantity squared. It's not a squared plus b squared because it's got that plus squared that doesn't make any sense. Okay? It's only if there's multiplication that you can apply to all the pieces. Okay? And then I think this is one of the ones that sometimes gets confusing. Negative exponents. Okay? Negative exponents, all you do is you flip the fraction and then make it positive. So if I had something like b to the negative 3, this would be the same as 1 over b to the positive 3. Okay? It doesn't make the actual number negative. It doesn't do any of that stuff. All it does is flip-flop the fraction. So you have a positive exponent in the denominator. And then the last piece kind of combines those 2 steps. And so if you end up with b over a to the negative n, we can apply that negative n to both parts, which makes both of them flip-flop. So something that was in the top would go to the bottom, something in the bottom would go to the top, and now it's all to the positive n. Okay? If you have issues with these as we're moving forwards in the next couple days, make sure you go back and check it out in the book. But these are all available in the book there. But we just want to do a quick recap on our exponential property. All right. Next type of property stuff that we're going to take a look at. Basic graph. What do these things even look like? Okay. Hopefully, we've seen this once before. We kind of talked about it. It looks like roller coaster, kind of a takeoff, right? So it starts very, very small. Never really gets to 0, right? Because that whole exponential property, if I had negative x values, it's just like 1 over something. So it gets really, really small, but never touches 0. So we have this horizontal asymptote, right, at y equals 0. In a basic world, your y-intercept is going to be at 1, because anything to the 0 power is 1. Okay? And then we have this, it's going to start to exponentially ramp up as our x's get larger. Okay? If that's going to be for any time your growth factor or your multiplier, this b value in that y equals a times b to the x, anytime b is greater than 1, we're growing, so we get this type of a look to it. Anytime b is between 0 and 1, that's where we're losing stuff. So like a ball bouncing, or like half-life stuff that we talked about with like medicine inside of a body, stuff like that. Things that are starting to decay over time. That'll give us this basic look where we end up with some sort of a value, and then it eventually starts to disappear. So now as these values get really big, the numbers for y get really, really small. Okay? So basic graphs. Then off of this, later on today, we'll take a look at, you can still use your shifts, horizontal and vertical. So stuff inside the function with the exponent will move us left and right. Things outside the function will move us up and down still. Something I wanted us just to kind of quickly look at and talk about. What is E? Okay, E is this number. We kind of talked about it the other day. More specifically, it's this thing we noticed with like population growth is a constant proportion to its current size, and so this rate of change. So we recognize this E piece as defined as x approaches infinity. This 1 plus 1 over x to the x starts to approach this constant number. So as we grow proportionally with ourselves, which is this 1 over x rate, we recognize that we start to approach this constant number, which is what E is. And those of us that don't know E, similar to pi, it's probably good to know it to at least 2 decimal places, is 2.72. Okay? It's like 2.718 something, something, something. But just like with pi, if you know it out to a couple places, you're in pretty good shape with it. Okay, so 2.72 is the constant for E. This is how they derive it, which is this 1 plus 1 over x to the x. So just so you know where they came up with the value for E. And then the last piece from 5.2 that we're going to look at, we're not going to talk about a whole lot in class today, but I'm going to make one video for today and tomorrow, or for Wednesday, is the idea of the uniqueness property. Okay, how many of us have had to deal with the uniqueness property before, where something has the same bases, their exponents must be the same? Thanks, Ben. Do I get to keep that for the day too? Thanks, dude. I've got 3 phones. I'm doing good today. All right. Okay, so the uniqueness property, right? This is that idea that if I had something like, actually, they've got the generic written there. So as an example, let's say I had something like 81 equals 27 to the x. Okay? You would be able to take that and find a similar base. So 81 can be written as 3 to what power? 4. Good. Okay, and 27 can be written as 3 to the 3rd. So this would be 3 to the 3rd to the x. So now we're going to use one of those exponential function properties we have, or one of those exponential properties. So this tells us that 3 to the 4th equals 3 to the 3x. Okay? So here's where this rule, our uniqueness property, comes in. If I have the same base, I can state that 4 must equal 3 to the x. Then we just have a really basic algebraic equation. So 4/3 would equal our x in this particular case. Okay? So that would be an example for us. We won't look at that in tonight's homework necessarily, but you will see it on Wednesday's homework. So tonight's homework will focus more on some of this stuff. Okay? We're going to do a lot of graphing. If I have no idea what something looks like, what's the easiest way to make its graph? Make a table. Okay? Start throwing numbers into it. Hopefully at some point along the way, somebody said, if you don't know what something looks like, build your x and your y and grab some values around 0. Okay? In this particular case, they're going to suggest you take -3, -2, -1, 0, 1, 2, and 3. Okay? And then you just plug them into the equation. So y equals 3 to the -3. Negative exponents makes us flip-flop this fraction. So this is the same as 1 over 3 cubed. 3 cubed is 27. Big or a small number? It's a pretty small number, right? Yeah. -2. This would be the same as 1 over 3 squared, which would be 1 over 9. Okay? Also a small number, but getting bigger. Okay, then 1 over 3. Anything to the 0 power is? 1. 3, 9, 27. Okay. So there's a little bit of pattern work to this. You've got some stuff that's 1 over all these numbers, and then the other version is all those numbers over 1. Okay, so as we start to put this together into a graph, we'll see that 1, 2, 3, 1, 2, 3. We'll call this 10, 20, 30. Okay, so as we plot these points, really, really small number. Okay, really close to 0. Still really small number. Still really small number. 1, 3, 9, 27. Okay, so all of a sudden this thing starts to ramp up on us. Now you've got 7 points. And even though we may not have known what it looks like, it starts to help you build the shape. And you're like, oh, hey, I had no idea what that looked like, but that table helps me build it. So generically, anytime you're stuck and you have no idea what something looks like, build a table. All right, so the next one we're going to take a look at. We're going to graph all these using our shifts. So hopefully from what we just did, we know that y equals 3x looks something like this. So what do we think y equals 3x plus 2 looks like? To the left, right, up, down, up, right? So it's on the outside here. So this is 3x. That's basically our purple graph. And then we're going to take all the purple stuff and just shift it up. We're going to add 2 to it. So instead of being 1/27, it's going to be 2 and 1/27. So basically what we've done is we've shifted this up 2 units, and we've moved this horizontal asymptote up, and then it's the exact same graph, just shifted up 2 units. Yep, so everything just gets moved up. Same idea as what we've had with other graphs with our parent functions. We're just still doing this stuff. So this was 3 to the x minus 2. So this was up in the exponent. That's where you're going to start to get the left and right shifts. Is if any of this stuff happens in the exponent, so part of that function, then we'll get some left and right shifts. Okay, speaking of which, a handful of the ones you're going to see will be, hey, match these up to graphs that already exist for you. So if we look at, I think B is the easiest one to start with, okay? What in B is going to tell me something fairly straightforward right away? It's going to be a -2, good, because my asymptote's down 2. So I know this has to match up with number 29. Perfect, thank you, Bailey. Nailed it. Okay, so B and 29 match up. So if we look at A doesn't have anything added to it. So I know it can't be 29, I know it can't be 30, I know it can't be 28. Okay? So it's got to be one of those other ones. Ben?
You just use the coordinate?
You could use some coordinates. That might help us. Which one do you think it is? What coordinate were you going to try to use?
Let's go with the 1, 1.
Okay, so 1, 1. How's that going to help us?
Because you have to come out and put it in as x and come out as 1.
Okay. What about that other coordinate point? Is there something there that might help us? 0, 3. It's our y-intercept in this case. Any guesses which one it would be? 25, 26, or 27 based on that coordinate point? I'm going to guess that because there's a 3 involved,
27.
it's probably 27. Okay? In fact, I know that this thing's being shifted left and right because of this action inside, and it's reflected because there's the negative. Okay? So this thing's been reflected it's shifted 1 unit left. So when this was, and we could check it just like Ben said, if we plugged in 0, 3 to the first power is 3. So we can check those points. Okay? Excellent. So that works for us. So 27 would match up with A. Okay? Good work. So these ones, you're going to still take a look at the parent function, identify some of the things we know about shifts left and right, some of the stretching stuff, and you'll be able to identify, hopefully, all the pieces we're looking at. Okay, next couple questions, very, very just elementary. Just type it into the calculator and it spits stuff out for you, okay? Exponential equations, some of this is really difficult, especially once you get into like decimals, to be able to do the exponents, especially when we're dealing with E all the time, because it's that 2.718, yada, 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 yada. So, what is E to the first? Just E, which, yeah, like Chris said, is 2.72 roughly. Good. And how about E to the 0? 1. Anything to the first power, or to the 0 power is 1. Okay, but if you start getting things like E to the 2.4, or something weird like that, just type it in the calculator and get decimal approximations. A lot of the exponential growth stuff will end up being decimal approximations. Last piece we're going to look at tonight is going to be graphing these. So you're going to have your shifts. You know that, well, first of all, do we know what e to the x looks like? We're going to graph that. We kind of do, right? What do you think it's going to look like? It's going to look like exponential. We just graphed y equals 3 to the x.
It's just like graphing y equals 2 whatever.
2.72 to the x, right? So is that going to be flatter or steeper? It's going to be flatter because it's less than 3. Good. So let's say this is our y equals 3 to the x that we just graphed. Okay? And then let's say that this is e to the x. E to the x would something like that. Okay? It won't get as small as fast, and it won't get as big as fast. So it kind of has that similar shape to it, but a little bit off with the skewness. And then if I want to shift this thing, and actually graph what that is, we're going to send it 3 units to the left and down 2 units. So this will be down 2 units, and it'll be over 3 units. Okay? Now, one thing I want you guys to kind of be aware of, because this was the common error I saw last year. When you shift this, usually that's a coordinate point, right? So you'd go over 3, down 2. Is there a coordinate point here?
No.
No, that's my asymptote. Where is the coordinate point at? It's up 1, because that's typically what our y-intercept is. So it's actually that coordinate point. The asymptote was shifted down 2. The y-intercept was shifted down 2, which gets us to -1. And then we have the exact same behavior. Okay? So just something to kind of be aware of. That shift left and right helps you with the asymptote and the y-intercept, but be aware that there's not actually a coordinate point at -3, -2. Cool. All right, so that's going to be it for today. And then we'll have a few other ones that I may make a quick video for tomorrow. But for the most part, that's what we're doing the next couple days.